Good afternoon. My name is Oliver Kühlert and I'm working at SYSGO in the technical product marketing team. Today I'd like to talk to you regarding how to increase the security in an embedded system by means of a hypervisor. So here is the agenda. I will quickly introduce to my company SYSGO. Then we will talk about security challenges and their solutions, which are in detail sandboxing. We are talking about denial of service attack, secure communication, secure boot, and finally there will be a short summary. Just a quick company introduction. SYSGO has been founded in 1991 and has started as a company providing services around embedded devices, software around embedded devices, mostly starting with Linux. We quite early had our own Linux distribution, Alinos. We were also acting as distributor for operating systems for avionics and other safety critical markets. This was a distribution coming from the US. And in the long time, we decided to provide our own European service operating system, which is called PICOS and is actually a hypervisor, and amongst other, it is ITAR free. Let's now start talking about security challenges and their solutions. So when it comes to avionics and security, there are certain assets to be protected in an airplane, which for example is the communication. Very important, the control within an airplane, and of course the data should be secured. Attack paths are a stack overflow, for example, or a buffer overflow. You can actually penetrate an aircraft by denial of service attacks. You can try any kind of intrusion or make man-in-the-middle attacks. There are several countermeasures, for example, sandboxing, the usage of robust APIs, resource partitioning. For the countermeasures against intrusions, you can use digital signed binaries and use a secure boot of chains. So other services you can implement are intrusion detection. For communication, you can use SSH communication or the TLS. One other thing is secure updates or even secure updates over the air, which more is of interesting in the automotive market, of course. When it comes to security, you can have multiple applications running at different terms of criticality, which is called a MILS, multiple independent level of security architecture. And there is common criteria, which is an IT standard to protect IT systems. And finally, there are several forms of certification kits which helps to go through a certification. Let's talk about sandboxing and start with a monolithic operating system, a traditional one. Here we have multiple address spaces, also called tasks or processes. So the Linux kernel itself has an address space and it has access to all applications, whether they are standard applications or they are critical applications. A typical access to a Linux system comes via one of the applications. Usually you take a huge one which has known vulnerabilities or zero-day exploits. And from this, you might get access to the kernel. Depending on which kernel you're using, which distribution, there are more or less exploits. The Linux kernel itself has about 30 million lines of code, so it's quite likely that you can find a way inside. From the Linux kernel, you then may have full access to all applications, as the Linux kernel typically has direct access to the address spaces of the running processes on top of Linux. This is another approach. Here we are running most of the system in user space. For example, the Linux kernel on the top left side is the one we were talking about before, and you have 30 million lines of code, but the difference here is that this part is now running in user space. Below that, you have the operating system, a hypervisor operating system. In the version I'm talking about today, we have a microkernel, which is about 30,000 lines of code, which is 1,000 times less than the Linux kernel. The microkernel itself is quite portable because it consists of an architecture support package and the platform support package. The first software that is being started by the microkernel is the so-called system software, and it implements partitioning by means of static allocation of the memory used by the system. That means once the system software has read the configuration and set up the hard partitioning, there is no longer memory propagation between the different partitions except for wanted communication or even shared memory. But this is configurable and not required. Once the system is running, you have the security environment and the safety function is shown here, running in completely separated and isolated partitions. Just a short comparison of partition and processes. So in both cases, it is about memory protection by separating virtual address space. But in a partition, you can have multiple address spaces. For example, in the running Linux kernel, the kernel itself is one, and it starts different address spaces for each process it is starting. If you only have a Linux kernel running, then you have one address space per process, typically. Partitions are set up statically, which means that once the system is running, there is no way to move any memory amongst the partitions. A Linux process typically has dynamic resource allocation, which means the memory being used can shrink or grow, depending on the situation. Even in a hypervisor, which is built for safety and security, even the memory resources that the kernel is using is separated, which means that if one partition requires the kernel to use a lot of memory for management services, then even this does not propagate to another partition because those kernel resources are strictly assigned to a dedicated partition. In a Linux system, the kernel resources are all the same in the entire address space. In partitions, the interrupts are handled by a thread model. That means if an interrupt occurs, it is forwarded to a user thread, which is waiting on an interrupt event. In a Linux system, you have the interrupts being handled in the kernel and usually forwarded to user space by means of signaling, for example. Finally, in a hypervisor kernel using time partitioning, even the time is partitioned, while in Linux you mostly have a round-robin scheduler mixed with a priority model. So now let's look into the setup we've had before. You can see the Linux on the top left. And in case it's being attacked, there is no way to propagate the attack to the security environment or the safety function. When we're talking about an airplane, this would mean that the features running on systems which are implemented in Linux kernel might fail, but the security environment cannot be accessed as well as the safety function, which might control the airplane in some way, are not affected if the Linux kernel has been attacked. In addition to that, in a hypervisor being used for the security and safety environment, the API is hardened against attack. So what does that mean? So whenever there is a system call which has been issued to the kernel, all the parameters are being checked before any action is being taken. This has been verified by an intense source code review and backed up by a common criteria EL3+ certification. This is possible because the microkernel itself is relatively small with 3000 lines of code only, and the criteria evaluation includes the system software, which is another 10,000 lines of code, which in this case is quite manageable. So let's talk about denial service attack. So even in case a system has no vulnerabilities, it can still be penetrated. So this can be done, for example, by stressing the CPU, by issuing a high volume of requests via network, for example, or by stressing the memory system by complex requests. In both of these cases, the safety or the controlling function and the security function of a system may fail. So how can you prevent this? You can use time partitioning to actually isolate the high effort being issued to the CPU. So if you have a Linux kernel, you would put it into a dedicated time partitioning, giving it only a certain amount of processor time. So for example, 20 time partition ticks. The security environment here would gather 40 time partition ticks, and for example, the safety function, which controls the airplane, 40 time partition ticks. So even if the Linux kernel is fully stressed, it will only use up the 20 time partition ticks, and both the security environment and the safety function will still run deterministic in their according time partitions. So let's take a look at the situation when you issue complex requests, which would stress the memory system. So in this case, we have the Linux kernel here on the left and the security and the safety function environment. As told before, the memory resources and as well as the kernel resources have been set up statically. That means if the Linux uses up all its memory, it will only use up the memory which is required or has been granted to the Linux system. The other partitions, like the security environment and safety function, will not be affected as they have their own statically assigned memory. Let's talk a little bit more about temporal separation by means of time partitioning. So you statically configure the order of time partition windows, and the time then will be statically assigned to the according time slot. That means if you start the system, there will be a periodic pattern, also called major time frame, starting with a Linux kernel in this example. It will get 40 time ticks, then the system will do a context switch and start the secure partitions, followed by the safe partitions. And if you have set a system with more operating system, then there will be any other system running as well. This is a very static and unflexible setup because of two reasons. In case that there is a reaction which must be done immediately of course, a safety function or a very secure situation, then the system might have to wait almost, or in the worst case, a full major time frame. In the hypervisor that I'm talking about, there is an additional time partition which is called time partition 0 and it's active at all the time, which means it's being overlaid to the current active time partition. The time partition 0 is actually a priority system, and you can set a fault handler at a very high priority, which means that a safety system may interrupt any partition at a given time. Of course, you should not do this with any partition, only the one which is really certified at the highest level in order to make sure that it won't shut down the system. By this, you can actually implement a fault handler that reacts immediately and makes sure that the system goes in a dedicated state if an unexpected behavior occurs. The other method that you can use with time partitioning 0 is setting up some services with a very, very low priority. In this case, this partitioning, which occupies this low priority, can reuse the time that is not being used by any other partition. This allows to build more efficient system with features that are not necessary to run a safety or security system. Please let me stress that this is totally optional, and we still guarantee that it won't affect the system, but of course you can still have cache effects. So case that you need to calculate a very accurate worst case execution time, you might not want to use up the background time. But if you design a system that has enough margins so that you actually can afford the misalignment of the cache, then this is a setup which gives you more efficient and optimized systems. In addition to this, the time partitioning handling has been integrated into multi-core handling. That means that you actually can configure a two-dimensional matrix setting up time partitioning and core usage at the same time. Actually, you can also combine processor cores, setting up a processor group, which means that, for example, you can use a SMP Linux on top of a resource partition which spawns multiple cores. In this case, both cores are actually being balanced and optimized in a very efficient way. This is a more deeper example about how time partitioning works with multiple processor cores and the opportunity to set up multiple time partitioning schemes that allows you to switch between different orders of time partition windows for different states of the system. For example, if the system boots up, you might want to have a different behavior, or in case if the system goes into a safe state or autonomous state, then you might want to have a different time partition scheme which is more adequate for the current situation. Finally, talking about secure communications. By default, when the hypervisor comes up, all resource partitions are completely isolated from each other, and there is no communication methods between the partitions at all, except you define wanted communications. So there are multiple ways. The first way is so-called queuing ports, and these queuing ports are defined according to a safety standard from the AVIONICS world called AIRWORTHINESS 653, and it allows unidirectional communications between partitions with the buffers. So it's methods based, and the communications buffered resides within the system software. The queuing ports are a one-to-one communication, and you can use blocking as well as non-blocking calls as an API. The other communication method are sampling ports. They are also AIRWORTHINESS 653 compliant, and they are a one-to-many communication method. That means that one source can be connected to multiple receivers. This only has a buffer depth of 1, which means there's only a current set of data buffered in the system software. The last communication method is the so-called file system, and it implies bidirectional communications between partitions, and it isn't as that safe or secure as the queuing ports and sampling ports are, but it allows more flexible in systems which need lower certifications, and it's a bit more performant. Finally, when you want to implement a data diode between different resource partitions, you could use queuing ports, but there are some pitfalls. So if you want to completely hide the timing behavior of a partition, make sure that you do not use blocking calls, because otherwise you would figure out the state of the sending partitions. In addition to that, to really make sure that you cannot get any information on the timing behavior of another partition, you should use strict time partitioning and clear and validate the data caches when you switch between the partitions. If you do so, you have strong memory segregation, and you can really make sure that the data is flowing only into one direction. Finally, if you need high performance, you can use shared memories between partitions. This can be set up by the system software at startup. It is the fastest communication method. You always must be aware that the granularity of shared memory is 1 page, and if you want to share content, you always should make sure that you do not have sensitive data inside the page you're sharing with the data you want to share. That seems to be obvious at the first glance, but in most cases it requires to write dedicated linker scripts, because from C you rarely have control where your data is being put in a system compiled and linked with a standard compiler. You can set access flags like read, write, and execute. And execute is interesting because by means of that you can execute code in shared memory. And this is interesting when you want to set up systems that you can update on the fly. So in this case, you will have a controlling partitions, and we can come to this a little bit later when we talk about system partition with enhanced privileges. The system partitions might shut down a other partition, change the executable code in the shared memory, and then restart the partition. When you do so, always make sure that you weigh the risk, and when you have partition with enhanced writes, make sure that those partitions are certified at the highest level and undergo strict development procedures. Let's quickly talk about secure boot and the chain of trust. So in the hypervisor we are currently talking about, and which is ARINC 653 compatible, it contains a health monitor subsystem. This subsystem is able to detect memory violations, processor exception, time partition violations, and it also allows you to inject errors. Once the health monitor has detected a problem, it can handle the problem at application level, which basically is sending an event to a handler thread, at partition level, which means to restart a partition, or at module level, which means to halt or restart the entire board. If we're talking about the avionics world and restart a complete board, of course you must make sure that you have a backup system running so that the backup system can take control of the aircraft while you restart the faulty module board. Talking about system partitions have enhanced privileges. They might start and stop other user partitions and even inspect or modify their memory by means of shared memories. So by this you can surveillance user partitions, you can implement intrusion detection systems, you might switch a system to fallback mode. For example, in case of a drone, you can shut down all the unnecessary communications and enable autonomous mode so that the aircraft can safely return home. And finally, it would also be possible to repurpose a partition by changing the executable code by means of shared memory. About the secure boot and chain of trust. So usually you start with trusted hardware, which has several kinds of HSM, like a TPM system on x86 or Trust Zone on ARM. The hardware checks the validity of the bootloader, which in many cases, for example, would be a U-boot. And this bootloader would then change the digital certificate of the operating system, which is then being started by the bootloader. In case of the hypervisor, the operating system would not immediately start the user partitions, but instead start one of the system partitions, which can actually check the integrity of the user partitions, which are typically a factor of 1000 bigger. So a system partition will do a complete security check. In a safety system, it will also do a built-in system test. Afterwards, the system partition either raises a memory event or would start the user partition, which then would take control over the airplane or provide communication features and set up the security environment. Just some hints on certification. So in terms of security, there is a new standard. It's the DIODE 326A, which is the first cybersecurity standard, and it has been backed up by the DIODE 560 standard, which actually is a practical guide to the new cybersecurity standard. And this DIODE 356A standard has a whole lot of checklists which helps you to set up aircrafts or airworthiness systems that follow standard procedures of security within an airplane. Very interestingly, this standard has an appendix which is a link to common criteria, and it helps you to point out the security assurance objectives, and you can cover about 60% of the security specific assurances by means of common criteria evaluations topics. Apart from that, there are other things you need to implement if you want to be DIODE 356A compliant, and amongst other, that is a security risk analysis and a refutation analysis. The refutation analysis is a bit new, and it helps you to identify vulnerabilities and to plan your penetration tests a little bit more in depth. And finally, the DIODE 356A standard helps you in setting up a safe defense in depth architecture by usage of independence, diversity, and isolation. Let's come to a quick summary. So, by means of virtualization, a hypervisor provides a summary. So, by means of virtualization, a hypervisor provides solutions for the most emerging security challenges. The partitioning mechanisms helps to isolate security attacks with regards to resource partitioning and time partitioning. And finally, the relatively new standard DIODE 356A helps to build you a bridge to common criteria evaluation to actually secure the systems of a flying airplane. So it's now time for you to ask questions, and thank you very much.